Good afternoon, sir.
Good afternoon. Namaste.
Namaste, sir. With the permission of Associate Dean, we'll start the program. Sir, may I start the program, sir? Associate Dean, sir. Prabhakar Reddy, sir. May I start the program, sir?
Hello, madam, you can proceed. Hello. Hello.
Sir, may I start the program, sir? May I start
Okay, madam, you
the
can
program,
proceed.
sir?
You can proceed.
Sir, you are audible. Thank you, sir. Thank you. Good afternoon to one and all. A warm welcome from the Department of Statistics and Computer Applications, SV Agriculture College, Acharya Engineering Agriculture University, Tirupati. Let me thank first our Honorable Vice Chancellor, Dr. A. Vishnuvardhan Reddy Garu, and respected Dean of Agriculture and Principal Investigator of IDP, Dr. P. Sudhakar, sir, and beloved Associate Dean, Dr. G. Prabhakar Reddy, sir, SB Agriculture College, Tirupati, and other university officers for giving us this opportunity to conduct this national webinar on the eve of Diamond Jubilee celebrations of Acharya N.G. Ranga Agriculture University. I profoundly thankful to today's speaker, Dr. Ranjit Kumar Pal sir, Associate Professor, ICAR, IASRI, New Delhi, for his kind acceptance to deliver a couple of lectures on this occasion. Now I request Dr. G. Prabhakar Reddy sir, Associate Dean, SV Agriculture College, Tirupati, for his welcome address. Over to Prabhakar Reddy sir. Unmute చేయండి మా సార్.
Will you allow? Madam, I was not allowed. Just now I got the connectivity. Am I audible? Hello.
Yes, sir. You are audible. Perfectly audible, sir. Please
Sir,
go
you
ahead.
are audible, sir. Please continue, sir.
Thank you, Dr. Lavanya Kumari. At the outset, I thank the university officers for having given me this opportunity for SV Agriculture College Tirupati to organize this national webinar. I welcome Dr. A. Vishnuvardhan Reddy sir, Honorable Vice Chancellor, Acharya N.G. Ranga Agriculture University, Dr. A. Sudhakar Garu, Dean of Agriculture, Dr. Ranjit Kumar Palji, Senior Scientist from IISRI, New Delhi, and Dr. V.S. Rao Garu, University Head and also Associate Dean, Agriculture College, Bapatla, and Dr. Lavanya Kumari, Assistant Professor Head and staff, Dr. Nafis, Umar, and other staff, and the faculty, and also participants who joined online across India for this national webinar on hybrid artificial intelligence models in agriculture. We know very well nowadays the artificial intelligence is a buzzword in most of the fields, wherein the artificial intelligence is being replacing the human interference to meet our requirements. In the same pattern, in agricultural field also, the involvement or application of artificial intelligence has become a routine practice, or most of the institutes are orienting their, one can say, the curriculum to the artificial intelligence mode. In the recent era, even ICR is also introducing this very latest techniques for blended learning and all. These artificial intelligence in the application in our agricultural field help to reduce the drudgery in human beings for attending different agricultural operations, starting from sowing of seed till harvesting. Here, I can say that our own university, Acharya N.G. Ranga Agriculture University, is also making some efforts to develop some robotic assisted, one can say, the reveeders, wherein there is a lot of application of artificial intelligence. Not only that, what we call the implements which reduce the drudgery in all the other aspects, like to monitor the crop condition and also to monitor the crop condition with respect to the what you call water requirement, and also to take the decisions on harvesting stage in different crops. There are many issues wherein there is a lot of application of artificial intelligence, wherein the human interference can be eliminated, wherein you can save time, and ultimately we can make decisions by getting the data and also capturing the data using different, one case that artificial intelligence mechanisms. And most of the universities are also orienting nowadays to introduce this artificial intelligence as a curriculum, and also to orient our education even for meeting different requirements. In this sense, whatever the webinar we have planned on hybrid artificial intelligence models, definitely they help us, because whatever the talks that have been planned, 2 talks have been planned as a part of this webinar. Definitely these 2 talks definitely open the insight into the artificial intelligence, wherein most of us are in nascent stage or a learning stage. Will ultimately, because today's speaker, Dr. Ranjit Kumar Palji, definitely he will throw the light on this new topic, wherein most of the institutes are looking for. I thank Dr. Lavanya Kumari for taking the initiative to organize this national webinar. Without wasting time, now I will hand over the mic to, or one can say that the program to Dr. Lavanya Kumari to conduct the further proceedings of this national webinar. Dr. Lavanya Kumari can proceed. Hello. Hello.
Sir.
You can proceed.
Yes,
You
sir.
can proceed. Okay. You can proceed and conduct the further proceedings.
Thank you, sir. Thank you for the.
You are muted, ma'am. You are muted. Yeah.
Am I now audible, sir? Yes.
You are audible. You can
Yes, sir.
proceed.
Thank you very much, sir, for your welcome address in this occasion and your continuous support in conducting academic activities in the Department of Statistics of Agriculture University, Tirupati especially. And now, by this, now I request our guest of honor, Dr. P. Sudhakar, sir, Dean of Agriculture and Principal Investigator of IDP for his valuable remarks on this occasion.
Okay, thank you, madam. Honorable Vice Chancellor, Acharya Engineering Agriculture University, and the Associate Dean of the Host Institute, Dr. Prabhakar Reddy, SV College, Tirupati, and also the host department, that is Department of Statistics and Computer Applications of University Head Srinivas Rao Garu, and also the Dr. P. Lavanya Kumari and his team. And I really appreciate the whole team for taking up this and most advanced and useful topic as a national webinar under the IDP. I'm really happy to know that. And this is a national webinar on hybrid artificial intelligence models in agriculture. Actually, it's need of the day. And we know by 2050, our production targets will be increased by 50%, as well as our land requirement is only 4%. So the actually target is huge and also it's frightening. Unlike other sectors, agriculture productivity forces different challenges and dimensions because of the crop growth, yield are deeply interconnected with the climate. So this is the major drawback when you compare to the other sectors. And no doubt our Indian scientists and farmers have made a tremendous efforts in making India as a self-sufficient, but already we are #1 in population in the world. So that means we should be more worried about our production targets by 2050. So despite of the more number of small and marginal farmers and huge number of small holdings, time has come to adopt the emerging technologies in Indian agriculture. And one of such emerging science, which is really penetrating into various sectors like service sectors, entertainment sectors, medical sectors, that's the nowadays the most listened the term is artificial intelligence. And this artificial intelligence and machine learning, generally called, are really pervasive very rapidly because of its robust applicability, especially in the problems that cannot be solved by the human beings as well as the traditional computing structures. And this, we know we have already traditional computing prediction models are already available in agriculture. But for climate predict models are there, yield models are there, pest and disease models are there. But I feel these are all the less explored in Indian agriculture. Still, we are lagging behind in understanding the, especially the crop weather relations, that is climate and crop relation is less understood. And all our prediction models also, especially the temperature and crop growth, still today we are very poor in understanding and also the prediction. So it's right time with the advent of these artificial intelligence hybrid models, I'm sure the future predictions related to the crop weather relations and other pests and disease and also different kinds of automation will be more realistic, and the data can be explored to improve the productivity in agriculture. At this juncture, I want once again congratulate the Department of Statistics and Computer Applications of ANGRU, as well as the Dr. Lavanya Kumari and his help. They almost like since 10 days, they have been working hard to conduct this webinar. And also, I'm really interested to listen to Dr. Ranjit Kumar Paul. Also, he is a concerned person in this. So really, since it's an emerging science, I'm really waiting to listen to the Dr. Paul's talk, sir. Thank you, Lavanya Kumar garu. Thank you for for giving me this opportunity. No? Thank you.
Thank you, sir. Thank you so much for your kind support and continuous encouragement for the development of this department in SV Agriculture College, sir. And for the sake of information and the dignitaries, the total number of registrations are around 309. Among them, 31% are faculty and 56% nearly from your students from MSc and PhD, and nearly 13% from others. It covers nearly 10 states, measuring AP, followed by UP and Tamil Nadu. By this, now I request Dr. V. Srinivas Rao, sir, University Head, Department of Statistics and Computer Applications, and Associate Dean, Agriculture College, Bapatla, for his opening remarks on today's lecture. Sir, over to
Thank you. Thank you, madam. Thank you, madam. First of all, I want to congratulate the SV Agricultural College, Department of Statistics and Computer Applications, who have taken the lead. And moreover, during the year of ANGRU Diamond Jubilee celebrations, I think it is the first program. And congratulations to Dr. Prabhakar Reddy garu and his team to take the initiation in the Diamond Jubilee year of ANGRU. And I want to thank our Honorable Vice Chancellor, sir, Dr. Vishnuvardhan Reddy garu. All the time he's encouraging the Department of Statistics and Computer Applications to do such programs, webinars, training programs and all. And I want to congratulate especially the Lavanya Kumari and Dr. Nafiz Umar for taking the initiation to have the beautiful program webinar like hybrid artificial intelligence models in agriculture. Comes to the topic really after the program of R, everybody is talking about artificial intelligence. Earlier, involved in the menu-driven programs like SPSS and other programs, at that time, to talking these programs are very difficult. But after R, we thank Ross Ika and Robert Gentleman, who are the developers of R programming. Because of them, we are applying all the statistical knowledge in various domains, not only in agriculture, industry or medical sciences and health sciences and all. Definitely nowadays the forecasting is very, very important. And by using these tools, like earlier we have only linear models, later we used non-linear models, then time series models like AR models, MA models, RMA models, then Arch-Garch models. Now this is the era of machine learning models, that is artificial intelligence models. And after this, we are using the hybrid models, because if the data follows some extent only linear, and after that it may not identify the pattern. So with the help of these hybrid models, especially like AN and artificial neural network models, or multi-layer perception, or long-term, short-term memory, LSTM models, and these combinations are really doing wonders to identify the pattern, to forecasting pests or diseases, or even the precipitation in any field. Because of these models, we are with very accurately, we are identifying the pattern and forecasting also. So really, it is a good beginning in the ANGRU. During the Diamond Jubilee celebrations, I know Dr. Ranjit Kumar Pal from several years. He is a very, very talented scientist in IASRI. He is working in forecasting division. And thank you, sir, for accepting our university request. And you are helping our PhD students also for their PhD guidance and all. I am once again thanking you all for giving the opportunity to be as a guest invitee in this webinar. And I once again congratulate our Department of Statistics faculty, especially Dr. Lavanya Kumari and Dr. Nafiz Umar, for taking initiation. Thank you. Thank you very much.
Thank you, sir, for your notable remarks on the topic and continuous support in developing the department, not only academics, but also in all other aspects, sir.
I thank our Dean of Agriculture, Dr. Sudhakar Garu, also forgotten, who is very instrumental and encouraging towards our Department of Statistics, because he's a good scientist in Acharya Engineering University. He published many papers. He knows the value of statistics. He is encouraging the Department of Statistics and Computer Applications. Thank you, sir. Thank you very much.
Thank you. Thank you so much, sir. Now I take opportunity and request Dr. Sheikh Nafiz Umar, Assistant Professor of this department, to introduce the speaker to the august audience. Over to the Nafiz Umar, sir.
Okay, madam. Thank you, madam. So it is a good evening to all. So it is my pleasure to welcome all the participants, national webinar on hybrid artificial intelligence models in agriculture. So I am a privilege to introduce to our invited speaker today, Dr. Ranjit Kumar Paul sir. He is a senior scientist at ICOR, Indian Agriculture Statistics Research Institute, New Delhi, in this national webinar on hybrid artificial intelligence models in agriculture. So he was visiting scientist at the Department of Economics, South Dakota State University, USA, published more than 180 research papers in national and international journals. He is an elected fellow of the National Academy of Agricultural Sciences. He is also fellow of Indian Society of Agricultural Statistics. He is a recipient of NAS Young Scientist Award in Social Sciences, the Young Scientist Award from Indian Society of Agricultural Statistics, Young Scientist Award from Society for Application of Statistics in Agriculture and Allied Sciences. He received ICAR Lal Bahadur Shastri Outstanding Young Scientist Award in Social Sciences. So he is actively involved in postgraduate teaching. Delivered several invited talks at the national, international conferences, workshops, and seminars. So he is guided 4 MSc students and 2 PhD students in agriculture statistics, and presently guiding 2 PhD students in the discipline of agriculture statistics. So he has published many R packages. According to Google Scholar, his total citations are 2599. The I-10 index is 60 and H index is 30. He is a recipient of Eminent Scientist Award. So in the year 2022, in the 4th International Conference of Global Efforts on Agriculture, Forestry, Environment, and Food Security. Sir, once again, thank you, sir, for accepting this webinar. Okay, sir, thank you. Thank you.
Thank you.
Thank you, sir, Dr. Nafiz Umar, sir, for your introduction about the speaker to the guests. Now over to the Ranjit sir for his talk. I request Ranjit sir to proceed further.
Yeah.
Thank you so much, sir. We are eagerly waiting for your talk, sir. As
Thank
per the previous beneficiary talks, we improved our quality in conducting the research in Anglo also.
Okay.
Especially in artificial intelligence and machine learning topic is concerned. Thank you so much.
Okay,
Please.
thank you. So, very good afternoon, everyone. Honorable Vice Chancellor of this university, Dr. A. Vishnuvardhan Reddy sir, the Dean of Agriculture and the guest of honor of today's webinar, Dr. P. Sudhakar sir, the Associate Dean, Dr. G. Prabhakar Reddy sir, the Associate Dean, Professor and University Head, Dr. D. Srinivasa Rao sir, Dr. Lavanya Kumari ma'am, the organizer, Dr. Nafiz Umar, the other staff of the organizing committee, dear participants, faculty members, staff, and dear students. A very good afternoon to all of you. I'm really overwhelmed by the nice gesture of the organizer. It's a great opportunity for me too to share a few of my past research experience in the field of artificial intelligence as well as the hybrid time series model for forecasting agricultural data, particularly the price data, yield, and pest prediction. So thank you very much, ma'am, for all your effort and for giving me this opportunity to share my experience in this particular field. So I'm just sharing my slide. Is it visible, ma'am?
Yes, sir, it is visible, sir. It
Okay,
is.
ma'am. So, so today's topic is on the hybrid artificial intelligence model and their application in agriculture. And I'll be sharing this slide as well as the R code, which will be developing or in the next session. So everything will get all the participants. So basically, it is universally true that the forecasting plays a crucial role in business, industry, government, different institutional planning, and all. And when we actually forecast, it can be made in different ways. Obviously, the choice of the method depends on the purpose, what is our purpose, and the importance of the forecast as well as the cost of alternative method. So resources is one of the most important factor when we actually go for developing a forecast model for forecasting any data set. Maybe it's a commodity price data, maybe yield data, maybe pest prediction, disease incidence, etc. Now, the empirical analysis, what we do for the agricultural series, particularly say agricultural commodity prices, they provide useful information that can be used to evaluate the performance of the empirical model. Now, when we talk about the time series models per se, the notable work by Box and Jenkins in 1970s in the name of autoregressive integrated moving average methodology comes in our mind, which has been a dominated time series analysis for the last several decades. But just like any other statistical parametric technique, this particular model is also based on some crucial assumptions. And the assumptions are the linearity assumption and the homoscedastic error variance of this particularly ADIMA model. But in most of the practical scenario, whenever we look at the data, maybe it is a price data or any other agricultural data, we see that they are not really linearly dependent over time. There may be some sudden hike in the data, or there may be a sudden dip in the data, which makes the assumptions of this methodology makes it quite impossible to deal with the series. This kind of series where there is a sudden hike in the data or there is a sudden dip in the data, which causes the volatility in it. And to accommodate this, what happens that this volatility sometimes is an integral part of the commodity trading and also the price analysis. In the last few decades, if we see at the literature, we'll see that much effort has been devoted towards the development of the forecasting or volatility model. And one of the notable work by Professor R.F. Angel in 1982, he developed this autoregressive conditional heteroscedastic model, which was introduced basically to provide the better estimate of the variance, leading to ultimately better assessment of the risk. But this particular ARCH model has also some limitations in the sense that the feature of ARCH to give satisfactory forecast only with a large number of the parameters, which necessitated the development of the generalized version of this model, which is named as generalized ARCH model, that was developed by Boltzmann in way back 1986. But all these are belonging to the parametric domain of the model. We know the individual drawback of the parametric model. There are certain assumptions to be fulfilled before we call for this parametric model. At the same time, we need to know what is the exact functional form between the variables we are dealing with. Sometimes it is also not possible to postulate the appropriate parametric form. In that case, we have alternate option is to call for some non-parametric approaches. Now, in the last few decades, particularly in the recent years, we can see that the machine learning techniques have drawn attentions of the researchers, and it has established itself as a serious contenders to the classical statistical model in the forecasting community. In the machine learning techniques, there are many machine learning techniques which have been widely used in the literature. Among them, the oldest is probably the neural network model. The neural network based models were incepted more than half a century ago. But the lack of processing capabilities and the availability of a huge quantity of the data, because to have a machine learning model or deep learning model to be applied on a data set, so we need to have a huge data set. We need to have large observations in the data set. And due to the lack of that, it hinders their wide range of application. Generally, the widely used machine learning techniques has been this artificial neural network. We have generalized regression neural network. We have random forest, support vector regression, etc. We have GBM also, that is gradient boosting machines, and so many. Now, beside this, all these particular technique, whatever machine learning techniques you have listed, and those who have not been listed here, all these machine learning techniques are basically a black box type or data-driven approach. So what happens? This data-driven non-parametric nonlinear models, they learn the stochastic dependency between the past and future value based on the historical data. So all the machine learning or deep learning technique, they basically learn the pattern existed in the data by the historical pattern, and it gives the future pattern from this. Another very powerful non-parametric approach has been the wavelet analysis. There are different other decomposition techniques. Probably we all know, we have heard about the Fourier decomposition or Fourier analysis. What a Fourier analysis does is that it tries to represent a particular function as a linear combination of the Fourier basis function, that is sine and cosine. There are two bases of Fourier. One is a sine function, another is a cosine function. So what it tries to do is that a particular function is represented as a linear combination of the sine and cosine function. Just like that, wavelet is also helpful in representing a complex function as a combination of the wavelet basis function. So the advantage in the wavelet is that, unlike in Fourier, where we have two basis functions, sine and cosine, in wavelet we have many basis functions, wavelet basis functions. So we have a larger subset, and from that subset we can choose the particular function or different functions to more appropriately represent our data sets we are dealing with. And there are different purposes of this particular technique also in statistics. One is denoising. Now, whenever we collect a data set, particularly when we deal with the time series data, we intuitively assume that the data is a noisy data. That means the actual signal is mixed up with the noise, and it is really difficult to extract that actual signal from the noisy data. For example, if you consider a price data over the past years or past months, we have a series, univariate series, and we assume that, or it is a fact that that particular series is mixed with the actual signal along with some noise. Now that noise part, how to remove that noise part? So wavelet is one of the efficient technique in denoising the series. That means it actually extracts the actual signal and extract the noise separately, so that with the actual signal extracted from this particular technique, we can go for prediction. And several other purposes can also be solved by using this wavelet. For example, we can go for the non-parametric function estimation. We can go for data compression and process synthesis. Now, combination of this decomposition, not only wavelet, there are other decompositions also. For example, we have SIMDAN decomposition. We have other kind of decomposition that IMF we get. Different decomposition techniques are available, which actually decompose the dataset into several parts, and those several parts can be treated as the representative of different components present in the time series data. We'll come into that. Now, once we decompose the dataset, then the noise of the noisy signal followed by application of the suitably chosen parametric or non-parametric approach. So the algorithm will be dealing with the details that how machine learning techniques and the different decomposition technique can be mixed up and followed by extracting the pattern existed in the actual series, representing it by means of different machine learning algorithms or machine learning techniques, and at the end of the day, by going for the inverse transformation or inverse wavelet transformation, we actually predict in terms of the actual series. Now, before we go for this algorithm, a very basic things for the students particularly, we have a time series model, we have a time series data. It is basically consisting of 4 components. So one component, we say it is trained. Obviously, there may be a long-term increase or decrease in the data set, which contributes towards trend. Then we have a seasonality. If we have a monthly data, if we have a weekly data or quarterly data, 6-monthly data, like that, we may experience seasonality. Then we have a component called cyclicity or cyclical component, when data exhibit rise and falls that are not of a fixed period. The cyclicity may not be of a fixed period. And obviously, the most important part or the necessity part is the irregular component, which actually is the unobserved component or goes to the noise part or error. So in any time series data must contain an irregular component, but it may not contain a cyclical component for seasonality. For example, if you are dealing with the yearly data, there is no question of seasonality coming into picture. But in yearly data, we may experience cyclicity also, but that may not be of the fixed period. In most of the data set, we may experience trend. Sometimes there may be a monotonic increasing trend or monotonic decreasing trend, or there may be some kind of ups and downs. So there may be localized trend, global trend, all those things. To visualize it, this is a time series, its fluctuations, and you can see the broader cycle. This is the cyclical component. The inside the smaller cycle, that is the seasonal component. And you know that in many of the agricultural data set, if we consider the commodity price data, any of the agricultural commodity price data, if we consider it as a monthly data, then we generally see seasonality in it, particularly in the perishable vegetable. Then the linear trend, we have just drawn a straight line trend, which just indicates a global increase in this particular series. And then irregular fluctuations, which is really unpredictable or unobserved, or they are basically considered as the noise. So these are the basic 4 components of any time series data. Now coming to the different category of the time series models. So we have a parametric domain, we have a non-parametric domain. We know the advantage and disadvantages of this particular domain. In parametric domain, we have the assumptions of particularly the distributional assumptions have to be fulfilled. And at the same time, we need to know what is the functional form. In non-parametric domain, there is as such no distributional assumption, as well as we do not need to have the functional form in hand to apply the non-parametric technique. Among the parametric technique, the well-known, I hope all of us know it. Among the parametric, we have 2 broad categories. One is the linear model, and another is the non-linear model. In the linear domain, we have ADIMA, that is called autoregressive integrated moving average model. This is for non-seasonal time series. That means when we deal with yearly data or even in monthly data, not all the series may exhibit seasonality. Some of the series may not exhibit seasonality at all. So in that case, also ADIMA may be suitable. Then we have a SARIMA model, that is seasonal ADIMA model, which obviously takes into consideration the seasonality part in the series. We have exponential smoothing and all other different parts of the linear domain. Then in the nonlinear counterpart, we have arch model, which we have already discussed. That way back in 1982, Professor R.F. Angel proposed this arch model to estimate the variance. Then we have guards model, the other families of the guards model like exponential guards. We have power guards, threshold guards, integrated guards. There are so many different nonlinear time series model exist in the literature. When you come to the non-parametric domain, we have particularly machine learning and deep learning techniques. In the machine learning techniques, we have ANN, artificial neural network, we have support vector regression, random forest, we have gradient boosting machines. And among the deep learning, we have LSTM, long short-term memory model. We have RNN, that is recurrent neural network. We have GRU, gradient recurrent unit, and different other parts, bidirectional LSTM, we have deep LSTM, like that. So different options are available under this non-parametric domain. Before we actually come to the hybrid method, we need to know that whether we are dealing with a single univariate time series or a multivariate time series, or we are trying to apply a standalone model like ADIMA, SARIMA, GARD, charge, or any machine learning techniques, or even we are trying to apply hybrid or ensemble of the techniques, we need to follow these 4 steps of model building always. So first of all, we need to identify the model. We need to estimate the parameters. We need to go for the diagnostic checking. That means examining the residuals, whether the model we have built is adequate or not. And then we go for the forecasting. So model identification, basically it tells us that what are the variables to be incorporated in the model. If I have a dependent variable, say Y, that is the price data, and what would be its determinant, what would be its factors to determine the prices. Obviously, the lagged values in case of the time series, when we deal with the time series data, we have actual series, we have the current observations, and when we develop the time series model, we also intuitively assume that future depends on past through present. That means if we want to predict the future, it must depends on past, but through present. So if YT is my present value, it definitely depends on the past values also. So the past values may be as factor, they may be considered as factors, and then how distant past we should consider. That is also one of the important criteria to consider. Those I mean, we have all applied ARIMO model at least. So in the ARIMO model, we know that how we can actually determine the number of lagged values. YT depends on YT minus 1, T minus 2, or how long, how distant past values we consider for developing the model. So these are all coming into the first category of model identification. That is the first stage. Once you identify the model by different criteria which are existing for different models, we go for the parameter estimate. Once we estimate the parameters, we go for the third stage, that is called examining the residuals or diagnostic checking. That is most important stage in any of the model building. So whenever we try to develop a model, because when we actually do the parametric modeling, you know that there is an error term appearing in the model that is called epsilon t. In general, we denote it as epsilon t, which is a noise basically. But in the parametric domain, what we assume that noise should be IID, right? That noise epsilon t should be IID with normal distribution with a zero mean and a constant variance sigma square. But that error is itself is unobserved. So how you can examine the different properties of that IID normality, right? To examine that, we need to fit the model. We need to get the residuals, and on the residuals part, we need to check whether all the assumptions are fulfilled or not. So that's why the third step of model building is the most important step in among these four steps. So when we are satisfied in the third stage, that is diagnostic checking, that all the whatever model we have developed, that model is adequate and the residuals are following the assumptions mean for the error term, then we go for the forecast. So these are the all basics. Now coming to the hybrid, when we actually try to ensemble different models, or when we actually try to make combination of different models, then how to go ahead? Because here also there are some assumptions, though there are not distributional assumptions which are very crucial for the parametric domain. In the non-parametric or hybrid kind of thing, we do not have that distributional assumption, but we have few assumptions to be fulfilled. This methodology was basically first proposed by Zhang in 2001. He proposed this approach that decomposes a time series into linear and nonlinear component. So what we are assuming is that we have a time series, we have observed data, and that time series is mixed up with linear and nonlinear component. We have a linear component in that, and we have a nonlinear component also in that particular series itself. So what we have to do is that we have to extract the linear and nonlinear components separately. We need to estimate those separately. We need to predict them. And then if we combine these two predictions, then we can get the prediction for the actual series. So this is the basic concept. So how we can represent that YT is my original series, and it can be represented as the sum of the two components. One is the linear part, another is the nonlinear part. LT, we have denoted it as LT, that is the linear part. Capital NT, which is a nonlinear part, we denote here. Now, these represent respectively the linear and nonlinear component. These two components are to be estimated from the data. So we have a data sets, but seeing the data, seeing the observations, you cannot actually visualize that which is the linear part in it and which is the nonlinear part in it. So we need to have some methodology. We need to have some algorithm to extract it. And one by one, we need to extract it. So how do we go ahead? Before that, we need to follow these assumptions. So what are these assumptions? The assumption is that this particular algorithm assumes that linear and nonlinear pattern of a series can be separately modeled by different model. We assume that this particular series is consisting of two parts. One is the linear, another is the nonlinear. And linear part can be modeled separately. Nonlinear part can be modeled separately. Second is that the relationship between linear and nonlinear component are additive. That means whatever components are existing in that particular observed series, linear and nonlinear, they must be additive in nature. So that individual component we can model independently, and then we add up the individual prediction to get the prediction in terms of the actual series. And the third one is that the residuals coming from the linear model will contain only the nonlinear part. So this is basically a very valid assumption that when a linear time series model is applied to a observed series. For example, I have an observed series, and on that I need to apply ARIMA model, the basic time series model ARIMA. Now we know that ARIMA is the linear model. If we follow the steps properly, if we develop the ARIMA model adequately, so whatever linear component exists in that particular observed series, that can be accommodated by using ARIMA model. And once we fit the series by using ARIMA model, whatever residual we are getting from fitted model, that residual will not contain any linear part. So that is that actually says the adequacy of the model development. That means we have developed our model, ARIMA model, that is a linear time series model, and whatever linear component was there, whatever linear pattern existed in my observed series, that pattern has been extracted adequately by using the linear model. So if anything remains in the residuals, if any information remains in the residuals, that is purely due to the nonlinearity. There is no linear part exist in that particular residual. Okay. Now, so these steps, if we go ahead by step, so first of all, we go for linear time series model, say ARIMA model we fit, simple ARIMA model we fit on the data set. In the next step, we obtain the residuals from the fitted linear model. As I told that if we have fitted our model adequately, if all the steps we have followed properly, if the model has been developed precisely, then the residuals will contain only the nonlinear part, or the residuals will contain only the part other than linearity, because linearity we have already extracted by using ARIMA. And if ARIMA is fitted adequately, then no linear component will be existed in the residual series of that fitted model. So ET we just extract that. Once we have fitted ARIMA model, we compute the residuals, that is ET, which is nothing but deviation from the actual and the prediction. Now this LT hat, this is the predicted value from the linear part. In the step 3, what we do, we diagnose these residuals. We investigate, we examine these residuals, whether any autocorrelation or any pattern existed in these residuals. If there is any pattern existed in the residuals, that might be due to the nonlinearity. Because as I told repeatedly, that the linear component has been extracted, and if ET, these residuals are white noise, that means they are IID noise, then there is no questions of any component present in that. That is purely unpredictable. If we have a residuals which is IID or which is white noise, that means they are independent, they are identically distributed, and they are random. So definitely they will be unpredictable. There is no information left in the residuals which can be extracted by using any model. Only when residuals are not white noise, only when there is any pattern existed in the residuals, we can think of applying some advanced model to extract the informations available in the residual series. So that's why diagnosis of the residuals is most important. That once we have fitted the model, we get the residuals from the model, we investigate the residuals, that what is left in that residuals. Is there any information left in the residuals? If yes, then we can go for applying some advanced technique, some advanced model, particularly to extract the nonlinear pattern existed in the residual series. And for that, it is not always possible to visualize the residuals and say that, okay, these residuals are nonlinear. It may not be always possible. We may not be that experienced to actually visualize the data and say that it is a nonlinear. Rather, we may rely on the test available. So one of the tests for testing this nonlinearity is the BTS test, which is very much available in any of the statistical software. R also. It was proposed in 1996 by Brock. This test actually test the null hypothesis that your observations are independent, or basically there is no nonlinearity. But the alternate hypothesis is that there is having some pattern existed in the data. So once the residuals have been identified, once the residuals have been examined and they confirm the nonlinearity, then we can think of applying some nonlinear model It may be from the parametric domain like arch, gauge, or any other family of the gauge model, like exponential gauge, power gauge, threshold gauge, integrated gauge. There are so many extensions of the gauge model. Or we can think of applying the machine learning and deep learning techniques to these residuals to extract the nonlinear pattern existed in it. So either we go for the parametric model like arch gauge, or we can go for machine learning or deep learning technique like ANN, SVR, RF, GBM, LSTM, RF, RNN, GRU, anything to extract the nonlinear part or to predict the nonlinear part. Finally, so we have assumed that initially that YT is LT plus NT. LT we have already estimated by using ARIMA model. Whatever was left in the residual series, that is nonlinearity, that we have now estimated by using the nonlinear time series model like our arch, gauge, ANN, or any deep learning technique, and that resulted in capital NT hat. So these two prediction we get, and if we sum this, or if you just combine these two prediction, then we can get the prediction for the actual series. Now this is summing the prediction or taking the equal weights to each of the prediction. This is a very crude way. I mean, there are a lot of questions on it, that why do we give equal weights to both the part? A data set may consist of mode of nonlinearity rather than linearity, or other way also, a data set may contains mostly linear, but a few portion or a very less amount of nonlinearity present in it. So in that case, we may better go for some weighted combination or giving some optimization of the weights to individual linear and nonlinear part. So that way we can actually increase the precision of the model. Now, the same thing, how we actually combine that, we have an actual series. We go for the linear component by using ARIMA. Nonlinear component, we may go for gauge. So combination of the ARIMA and gauge. This is hybrid model or combination of the model, whatever we say. And then we just go for the simple sum, arithmetic sum, and we get the final forecast. Similarly, instead of gauge, your nonlinear component we can extract or we can predict for using ANN or any other model, SBR, RF, GBM, or any other deep learning technique also. Then accordingly, the linear part and nonlinear part will be predicted by the respective models. And then at the end of the day, we go for arithmetic summing of this individual part to get the forecast for the actual series. Now, a simple example of this, just how it increases the gain in precision of our forecast. That we have some potato price data, and these are very well known, that how we go for the accuracy measurements or empirical comparison of the different models we build up. So there are lots of criteria. In general, we do not go for a individual criteria. It is better to go along with more than one criteria, so that your model selection is to some extent robust. We have different criteria, like here we have reported two, that is MAP, mean absolute prediction error. We have root mean square error. We have MAC, that is mean square error. We have mean absolute error, MAE. We have mean error, and several others also. So in R, whenever we'll be doing, we will be seeing that if we go for the accuracy, a simple keyword or a simple function, we get the several accuracy measurements for testing the accuracy of the model. So it is always better to go for more than one accuracy measurement, so that our model, whichever we are going to select, that remains consistent and robust to some extent. So without going into the details of this, if we have understood the methodology well, the algorithm well, then we can just understand by visualizing this table that if we go for a simple advancement in the model, if we go for simple combination of the different models, then we can increase the precision or gain in accuracy in the model development. So you can see that this particular data we'll also see in the practical in the second session, that if we go for application of the ARIMA, obviously it is a monthly data, 2006 starting, and the last 12 observations, 1 year whole data we have kept for validation purpose. So ARIMA we have applied, it gives our 33% error. When we incorporate the seasonality, because potato and all these data sets are too much seasonal. So seasonality, if we can take care, then it reduces that percentage error to 18%. Then combination of the ARIMA and gauge, we go ahead it again reduces it to some extent. Then ARIMA ANN. So it is almost same, that combination of the ARIMA guards or ARIMA ANN almost same for this particular data. Then coming to ARIMA X, whenever we have information regarding the other factor. For example, initially we have discussed that we have a time series data, say price of a particular commodity over years or over the months, but that price depends on several other factors. It may depends on the arrival, mostly that what is the amount of that particular commodity arriving in the market. There is generally, from economic point of view, there is a negative relationship between the price and arrival. If the arrival is high, then price is low. That is negatively related. So if we have the information on the second variable, which we think that it is most important factor in governing the response variable, and incorporation of that auxiliary information may increase the accuracy in your forecast. So ARIMA X is the arrival here, or you may incorporate the rainfall or any other things which you think that may be a governing factor for governing the response variable. So gradually, when we are actually increasing the, when we actually incorporating the different information in the model, or we are going for the different combination of the model in order to pick up the linear and nonlinear parts separately, and finally combining those two predictions to get the prediction for the actual series, we are seeing that there is a subsequent increase in precision or subsequent increase in gain in accuracy in the model. Then in the similar pattern, as we have told, because just one decomposition technique I shall introduce, there are several other decomposition techniques which can be applied as well, and they may be combined with different machine learning and deep learning techniques. So one of the technique is wavelets. As why I am introducing or I am describing is that it is, though it looks like mathematically difficult, but it is really simple to apply, as because all R packages and codes are available in hand. So whatever, for example, if you want to go into the deeper of the machine learning and deep learning, their architecture is also not that simple, but it looks simple to us because the ready-made code is available, and the default parameter and hyperparameter values can give you gain in accuracy. So if you just tune the model properly, if we train the data properly, we can get a significant gain in the accuracy measurement. So as we told initially, that wavelet is basically just like Fourier analysis. Fourier analysis represents a function in terms of the linear combination of the sine and cosine function. Similar to that, wavelet represents a function in terms of the wavelet basis functions. So for example, psi dot, if it is a real valued function, we say that if it satisfies these two property, that integral of psi is 0 and integrate the square of the integration is 1. If these two properties are satisfied for this particular function psi, then we say that this is a wavelet. Okay, and this wavelet, it has come from this wave. It has a kind of oscillation about 0. So just about 0, it oscillates, and by this property, we more appropriately represent the pattern existed in the data by suitably choosing the wavelet filters and the level of decomposition. A good description of this particular method can be found in this, among them, this Percival and Walden book in 2000. It's really important. It's really details the application of the wavelets in time series domain and the forecasting. Now, just to have a basic idea of it without going into the mathematical detail, those who are interested in mathematical derivation, they can refer to this particular book I told, Percival and Walden in 2000. So here what we do is that we have an original series X. In a very simple way, we try to understand that X is the original series. That X is decomposed into two components first. Our interest is that we have a series and we need to denoise that. Denoise means we have a series which is mixed up with the noise and actual signal. Our interest is that how to extract that actual signal from that noisy data. And if we can do that, if we can extract the actual signal from the noisy data, then if we apply the model to the actual signal, our prediction accuracy will automatically increase. So that's our main motto in decomposition. So what we do in the first hand, X is decomposed into two parts. we call V1 represented as V1 and W1. W1 is called the wavelet coefficients, or we say it as detail coefficient. And V1, this is the smooth part. That means a time series, it is having an irregular component and one smooth part, kind of train. So if you just visualize a time series, any of the time series, it has some kind of pattern, maybe some ups and downs, and there is an increase with that. So it will have some smooth part, which may be a train kind of thing, and it may have some irregular part in it, which may be kind of zigzag in nature. So that nature is W1, and the smooth part is V1. Again, in the second state, this V1 is again bifurcated or decomposed into W2 and V2. Like that, we go ahead in the level of decomposition. Now, how to go ahead, where to stop? Generally, if a series is represented as, say, 2 to the power j, the number of observations is represented as 2 to the power j. For example, I have 64 observations. So 2 to the power 6. 2 to the power 6 is probably 64. So the level of decomposition would be 6 at max, or below that also we can consider. So what we are getting at the end of the day, we are getting from X, we are getting several series. From an individual series, we are getting several series. And we assume that, so these are different component, different way of decomposition. One is DWT and MODWT. I'm not going into that detail, just to make it very simple, that there are two ways. One is DWT, that is discrete wavelet transform, which is applicable only when your series is of length power of 2. That means if we have a series of length 64, if we have a series of length 128, 256, 512, 1024, like that, the power of 2, then we can go for DWT. Otherwise, for any integer numbered time series, any time series of any integer length, say 100 observation, 200 observation, we go for MODWT. That is called maximal overlap discrete wavelet transform. Now, what we are actually getting from here, from the X series, we have started with X. We have original X actual series, univariate time series, maybe of 100 observations are there in that particular series. So what we are getting after decomposition is that from a single series, we are getting different sub-series. Each of the series is having the same length. If X is of 100 observation, W1, the lowest level detail component, or wavelet component is also having 100 observation. Each one is a vector 1. W1 is also a vector of 100 observation. W2 is also a vector of 100 observation, like that. That 100 is just your length of the series. If you started the length of the series as 200, then each of these vector will have 200 observation. So W1 will be the detailed one. Little smoother is W2, little smoother is W3. Like that, as we go ahead, the last component Vj, that is the smoothest part. That is the trend of the data. So the beauty of this is that we have started with a single series and we have ended up with these many series. If we have, say, 4 level of decomposition, so 5 series we will be getting. If we consider capital J is 4, so we get W1, W2, W3, W4, and V4. These 5 series we can get. So from one series, we are getting 5 series. And each of these 5 series exhibit different pattern. So in the original series, we have mixed up pattern. We have linear pattern, non-linear complexity. We have a localized trend. We have global trend, like that. So different patterns are mixed up in a particular series. Now, what we are doing, we are just decomposing that particular series into several components. Each component or each of the sub-series will have a distinct pattern existed in the series. That means what we are doing, we are basically extracting the different pattern and storing it in the different variable. Now, individual sub-series can be modeled separately. So, for example, W1, it will be more irregular component, more zigzag nature, more of noisy kind of thing. So, may not be any model will be most suitable for that particular data to predict some. So, based on the nature existed in that data, based on the pattern existed in that particular component, we can apply the different models. For example, we apply guards model. For example, in W2, we apply guards, whatever it is appropriate. We may, maybe ARIMA is appropriate for W2. So ARIMA we can apply. W3 maybe have ARIMA like that. So whatever model is appropriate in each of the component, we treat each of the sub-series as a separate series. Now you consider modeling of a individual series by any of the measure, any of the means. Maybe parametric modeling or non-parametric modeling like lesson learning, deep learning like that. And then predict each component separately by using separate models. W1 is predicted by using Gart's model or whatever it is. W2 is predicted like that. And we just store W1 prediction, W2 prediction like that. Each of these series is of the same length as X. Now, all the series prediction we got, that means all the different pattern existed in the series, we extracted and predicted. And then we go for the inverse wavelet transform to get the prediction for the actual series. So this way is some significant amount in accuracy measurements we can gain, and we'll just see it in practical part also. Now here comes, there are others. So in this particular algorithm, what we have done, we have just given the parametric domain that we have decomposed a series, individual sub-series we have got, and on individual component we have applied different parametric model. Here, just an example, I have written ARIMA Garts. It may be anything. Based on the pattern existed in the data, we just call for the best model to be applied to extract the pattern in that particular component and then predict it. And the end of the day, we just go for inverse kind of transformation. It is available very much in this software. We have also made the package and we get the prediction for the actual series. Now to incorporate the ANN in it, for example, we have decomposed the series and ANN can be applied in two ways on the decomposed series. One is called, we are saying it as wavelet ANN hybrid. Another, we are saying it at wavelet neural network. So approach 1 and approach 2. What is the approach 1? The left-hand side, we apply the wavelet to decompose the series. One series is decomposed in several components. Each of the component is fitted in the ANN. Each of the component, we treat it as independent series. Each component is fitted through ANN. We get the prediction by using ANN and then combine all these predictions to get the prediction for the actual series. So this is one. Second part is that in the wavelet neural network, what we do here, we also go for this wavelet decomposition. But after that, when we are fitting ANN, in ANN, in the hidden layer, we have activation functions to be called for. When we actually apply ANN, artificial neural network, we have an input layer, we have a hidden layer, we have an output layer. Three basic layers are there in ANN. From the input layer, we are just giving the input to the system. Those inputs will be in terms of the lag. For example, if we are dealing with the univariate time series model, so YT minus 1, YT minus 2, like that, different lags will be considered as input in the ANN. Then in the hidden layer, there is activation function. Different activation functions are available. Generally, we have the sigmoid activation function, right? That activation function is called for by default. And then activation function represents the data and then it goes to the output layer. But in case of the wavelet neural network, what we are doing in the ANN, we can actually call for some wavelet basis function as the activation function. Instead of going for the activation function of the ANN, the usual activation function like sigmoid, instead of that, what we are trying to do is that we are trying to call these activation functions of the wavelet basis functions. And there are lots of wavelet basis functions which can actually more appropriately represent the series. So in a more detailed way, if we just want to see, we have input data, we go for the decomposition from an individual series, we are getting different subseries. Say here we are representing as D1, you consider D as W and S as V. So D1, D2, DP, these are nothing but W1, W2, WP. Individual series fitted with ANN, get the prediction, go for inverse wavelet transformation to get the prediction in terms of the actual series. This is the first approach. Second approach, what happened? Here comes the second approach, that when we actually go for the application of the ANN, then in the hidden layer, we have the activation function. Instead of calling for the usual activation function, which is sigmoid in general, instead of calling for that, we are calling for activation function picked up from the wavelet basis. So generally we have morlet, we have simlet, list asymmetric kind of thing, different options we have available, and from those available functions we can pick up that also based on the nature of the data, because whenever we actually try to analyze our data set, first of all we try to visualize the data, that what is the nature existed in the data set. We try to gauge the nature of the data, whether the pattern is linear, whether the pattern is some extent mimicking the pattern of quadratic kind of function, or there is a sigmoid kind of thing, or there is any other growth model which has more appropriate similarity with the pattern existed in my data. So accordingly, we just gauge that particular function, because whatever modeling we are doing, all are kind of trial and error basis. We just try to appropriately choose the function. We may not be very accurate to choosing the function, but by visualizing the data set, by visualizing the pattern existed in the data set, and by visualizing the functional form, whatever activation function we are having, and the most appropriately choose. Of course, there are some other criteria based on the nature of the data. So this way, we can apply the wavelet and artificial neural network to combine these and to get the prediction for the increasing accuracy. Now, how this decomposition looks like visually. So, for example, we have gone for the 4 level of decomposition for a univariate time series data. The lowermost part is the detail part, that is W1. You go up W2, W3, W4, G4. As we go up, we will see that there is a kind of smooth version of this or the smoothest kind of pattern existing. So in a series, we have irregular part, as we have discussed, that will be stored in W1, W2, W3 like that. And whenever we come to the smoothest part, which basically represents the global trend in the data, that goes to the V4, that is the smoothest part. So this way, your individual component will look like, and individual component, you can treat it as separate variable, and based on the pattern in it, we can actually call for the individual model to be applied on it to get the prediction. And at the end of the day, we just go for the inverse kind of transformation to get the prediction of the actual series. Now on individual sub-component, we have chosen different models. Wherever GARCH is applicable, we have chosen GARCH. Wherever ANN is applicable, we can choose ANN. Wherever ADIMA is applicable, we can choose ADIMA and go for the fitting. And then we just have in comparison, we have done 3 years, I think it is in 2019. So 4 years back. And here we reported that when you actually go for WebLearn, that is wavelet along with ANN, but coupled with choosing the activation function from the wavelet domain, not the usual activation function of the ANN, it resulted a significant increase in the accuracy measurement for all the particular criteria. Then similar kind of thing, we can go for the wavelet SVR, the other the machine learning techniques. We have talked about artificial neural network here, but we have other machine learning technique and deep learning technique also. Just to go it quickly. So this is the wavelet decomposition looks like. And any other decomposition also, it will look like just similar pattern, that we have original series. Any of the plot you can see, the the lowermost plot is the original series, the actual time plot of the Y. It may be here it is a price data. You may consider it any time series data. So the lowermost plot of any of the plot you can just look at. The lowermost small plot is the time plot of the actual series, the response variable. As you go up, the W1, W2, W3, W4, W5, W6, and V6. As we go up, we are getting the component smoother and smoother, and the last component will be the smoothest one. So that is the smoothest component extracted from the actual series, which represents the global trend present in the data. So the beauty of this is that unlike the linear trend, because as we have discussed initially, that a data set may not contain always a linear monotonic trend. There may be some kind of localized trend. in some particular domain, in some particular time domain, the trend may be say decreasing, then it may be increasing, then says straight line, then again increasing, decreasing, like that. So these small domain trend, these are called localized trend. So here the feature or the nice feature is that individual localized trend can also be detected. So you can see the lower part. Say for example, W1, any of this particular plot, if you look at the W1, wherever there is a virtual clustering of the higher value, in that particular time epoch, you can choose that there may be sudden up or there may be a sudden jump in the data. So you can just compare with the actual series, which is the lowermost small plot represented in terms of Y. Wherever there is a sudden jump or there is a sudden dip in the data, that is being represented as the virtual clustering of the coefficients of W1. So this basically gives us to pinpoint where the disturbances arises in which particular time epochs, and accordingly we can give some extra causes during the model building. Maybe there is some intervention appears in that particular time domain or time epochs. So accordingly, we can go for some kind of intervention type of model so that the model accuracy increases. And this way, individual component can be described. And then, there are different filters available. As I told that you have lots of filters available in wavelets. You have a lot of, a larger subset wherefrom we can choose different functions to represent your data more accurately. So accordingly, you just choose that. For the time being, those who will be using the first time, don't bother about the choosing of function. The default function will also serve the purpose. It will definitely increase the accuracy of the model as compared to the usual traditional machine learning or traditional time series model, classical time series model. So, but the most important part is just like machine learning, deep learning, and all other machine dependent models, training is most important. That we need to fine tune the parameter. For example, when we apply for ANN model, the artificial neural network model, we have different parameters and hyperparameters to be tuned, right? For example, the parameters maybe say P equals to how many lags you have to include, right? Then what is the hidden layer size? What is the iteration? What is the learning rate? At which learning rate you need to learn the data set? So all these things we need to tune properly. We need to give a range. We need to look at the MSE, mean square error, or any other performance criteria to reach to the optimized values of individual parameter and hyperparameters to finally come out with the best model. So that is most important for any machine learning or deep learning technique. So merely going for default parameter may not serve the purpose. Rather, we need to go for fine-tuning it by properly training the data. And whenever we go for application of this time series model, machine learning and deep learning and hybrid technique to our time series model, every time series, obviously it has to be divided into two parts. One is a training and testing. That is a must for either in classical time series or any non-parametric time domain. So on the training part, you have to train the data, you have to train the model properly. And then in the testing, you have to validate the model. So we need to take extra caution because sometimes in some machine learning techniques, it may overfit the data, particularly random forest. We have experienced that in case of the random forest, if we use it for the prediction purpose, sometimes it may overfit the data. In that case, we need to properly train the data so that it remains consistent for both training as well as testing part. So this particular thing is available in this soft computing we have published. And then different models we have to chosen based on the performance criteria. You have different performance criteria. Here, for example, instead of wavelet ANN, you can go for wavelet LSTM also, or individual application of the LSTM, that is long short-term memory model that is called, under the domain of deep learning technique. We have applied individual ANN also, and either RMSE or MAD or MAP, as I told initially that no, never you go for a single criteria to choose the best model. It is always better to go for simultaneous criteria, because a single criteria may, by chance, it may appear that your model is good. But always we try to go for more than one criteria and validate it for more than one data set, so that the consistency and robustness of this particular model remains. Similar to that, you can apply different models. For example, you can go for wavelet, you can go for ADIMA, GARCH, and ANN. Combination of these wavelet, ADIMA, GARCH, and ANN. 4 models. So what we are doing, we have a time series data, go for decomposition, individual detail component, individual smooth component you are getting. On individual detail component, either you go for feature selection by maybe PCA or some other feature selection technique. Then individually selected features, we applied the ANN. On the other hand, the individual smooth component, we go for application of the ADIMA, GARCH, and other models. So different models are applied on this component, and then we go for optimizing the weights to be allotted to different prediction coming out from the different model to get the prediction. So all these have made the software also. So only thing is that what happens in the era of computer, in this particular era of computing facility, even 1% gain in accuracy, if it results, then also it is a significant gain. Because only thing what we need to do is that we need to load a package, we need to call for a particular function to be applied on our data in order to increase the gap, that gain, nothing else. In more detail, we can also apply some. Here S means for the SVR, support vector regression. So we can go for wavelet decomposition followed by ADIMA, then GARCH, we have support vector regression. Apply those model individual component, or on the same component also we can apply different models, and then we can go for weighted combination of the prediction coming out from different models, and that weights, whatever weight we are getting, that weight is determined by some optimization criteria. Okay, then the same thing we have applied, and then everywhere we'll see that whenever we apply some kind of decomposition technique followed by application of the machine learning or deep learning technique, unanimously, irrespective of the data set, irrespective of the markets we are concerning, that is outperforming the individual standalone model. So it is always better to go for combination model or hybrid kind of model based on machine learning or deep learning, or combination of the machine learning, deep learning, as well as classical time series. But the optimization needs to be properly done. That means which particular part will be given more weightage, which particular part will be given lesser weight, that has to be optimized by using some optimization technique. The last part of this presentation, I will show that how this is another decomposition, that instead of wavelet, we can go for other decomposition, like we have SIMNAN, from where we can get different IMF. Individual IMF can be modeled by different models. Here we have applied LSTM, we have applied GRU, and on the right hand side you can see ADIMA, GARCH, LSTM, GRU, these different machine learning, deep learning, as well as the classical time series model. So all can be applied, and then they can be combined using the optimization technique to get the best weightage to be allotted to individual counterpart. This we have applied recently for a rainfall data in 3 subdivisions, and as usual, that whenever we combine the different models, their accuracy is outperformed. Their accuracy is really significantly higher than that of the individual standalone model, even that it is deep learning. For example, LSTM is a deep learning model, GRU is the deep learning model, but when you actually go for the combination of this, you can result in from 22 to 13% or 16 to 8%, like that percentage error in that particular model. And there are different criteria, there are different ways to represent your prediction accuracy or accuracy measurements. One of those is the visual plot, because it is always better to represent the accuracy in terms of the plot rather than the table. For example, this Taylor diagram, you can see any of the, for example, the left-hand side plot, you can see the individual model here. 4, 6, 8, 10. Total 10 models have been applied. Okay, and the correlation is basically the association between the predicted value and the actual series. So how much accurate your prediction is. So by this way, you can represent more accurately, or you can actually get the attention of the readers more towards this particular plot to measure the accuracy of the different models. So here you can see this green button. This is Simdan based decomposition followed by AdaBoost and GRU application. That is great. The deep learning technique. So this model is giving you the most accurate or the highest accuracy in the prediction. The correlation between the prediction and actual is almost at the tune of more than 0.96, like that. Whereas the other model, even LSTM, it goes around 0.6 or 0.7. So it is a general practice that if you have sufficient observations in hand, then your machine learning model will generally outperform the classical time series model. Again, deep learning model will outperform the machine learning model. That means deep learning accuracy will be better than machine learning. Machine learning accuracy will be better than classical. In general, this is the trend. But obviously, here lies one assumption that if for the parametric counterpart, all the assumptions are fulfilled, then parametric model will be the best. It is very true for any statistical methodology that if all the assumptions are met, all the assumptions are satisfied, then the parametric model will be the best one. But in general, in reality, in practical data set, we hardly see that assumptions are fulfilled. Either the data will have certain high or certain deep in the data. So obviously there may be a non-linearity appearing in the data set or non-normality appearing in the data set, which results in violation of the usual assumptions of the classical time series model and which insists us to go for the machine learning and deep learning. Last 1 minute, I'll just discuss on this. This is our recent work that OptiSemble forecasting. Only in the last month, it is published in Journal of Supercomputing. So here what we have done is, we have a time series data. We have applied 13 models, model building, you can see 13 models. We have used 20 optimization techniques. Out of those 20 optimization techniques, the 13 models will be assigned a particular weight to the predicted values, and then final prediction will be computed based on the weighted optimization. So this is basic algorithm, and these are the different models which we have taken into consideration. All these are available in the R package. One R package has been recently released. We have released that OptiSemble forecasting, where you have to put the data set. The data will be fed with these 13 models, starting from ARIMA, error trend seasonality, TBATS model, ANN, SBR, random forest, K nearest neighbor, XGBoost, and then in the deep learning model, we have used RNN, GRU, LSTM, bidirectional LSTM, and deep LSTM. All these 13 models will be applied to your data, whatever data input you give, and then followed by, after you get the prediction by using 13 models, then the prediction will be weighted based on these 20 optimization techniques. So these are the 20 optimization technique which has been listed in that package, starting from your artificial bee colony to well optimization. Almost all the available optimization techniques for optimizing the weights for a time series setup has been incorporated, and then final prediction, it will give you that which combination or which particular optimization technique gives us the best weight to be assigned to individual 13 models to get the optimum prediction. And this way we have shown that, say for example, this way how it looks like, that you give a data set for a particular market. These are the feature selection kind of thing, that a set of the model will be selected, where these are the most important models where the weights will be higher, and in others model the weight will be lesser side. Accordingly, the models will be selected and weight will be assigned. And then you can just get the performance criteria measurement. Even almost all the optimization based ensemble model outperforms the individual counterpart. Either you go for the classical time series model, machine learning ML model, or deep learning DL model, all the optimization technique except one FFA, we concluded that this optimization is not up to the mark. We may not use this one. Other than this, all other optimization technique has outperformed the individual counterpart. And then, as we told, that the visualization is most important with compared to the value. So you can just go for these different kind of plots. We can get it from R, that to nicely visualize the prediction accuracy for different model. So here you can see we have this. This one is the ensemble model, the first plot. Second plot is the deep learning model. Third one is the machine learning, and fourth one is the traditional. As the size of the plot, the shaded area is shrinking. That means your prediction accuracy is increasing. So, for example, the traditional model, the prediction accuracy is higher. I mean, the lowest one, the error percentage is highest, followed by machine learning, then deep learning, then your ensemble counterpart. That means your hybrid kind of model. So yeah, that's the basic funda for this, and different R packages. All these packages are available. I will share with you all. These are available, and it's really easy to apply because we need not to go into we need not to have programming knowledge. We just want to call that particular package and call a particular function to apply on your data set. So to conclude this, individual Box-Jenkins-Arima methodology is most popular whenever we talk about the time series. But in many of the practical situations, we see that the assumptions are violated, so we cannot apply this model. Then we go for the nonlinear counterpart. But whenever the functional form is not available to us, we go for the machine learning and deep learning kind of thing. And then if we go for the hybrid or ensemble kind of model, followed by different decomposition technique, or even if you do not go for the decomposition, you just combine different model, classical time series, machine learning, and deep learning, get the weighted ensemble of that model to get the prediction. It will always outperform the individual counterpart, or that is individual classical, machine learning, or deep learning technique. So yeah, that's all. These are the different references. I shall share this slide with you, ma'am. Then you can share with the participants if they want, and they can take it out.
Sure, sir. Sure.
Thank you, ma'am. Thank you.
Thank you, sir. Thank you. Thank you. We were loaded with heavy loads regarding modeling and forecasting is concerned. And it is very interesting, sir, wavelet methodology is concerned. It is very new to us. Actually, we are working with the linear, non-linear, parametric, of course, machine learning models.
Yes, ma'am.
Sometimes hybrid models are two-stage models. But
Right.
I have many doubts, sir. Apart from just, I can pose very few doubts now.
Yes.
Can I continue, sir?
Sure, ma'am. Sure,
Sir,
please.
my question is, what is the basic difference between wavelet and cyclical? What you are telling, oscillation over zero will become wavelet. And it is showing the mean is zero and the variance somehow is one. If I am right, sir.
Exactly. Yes.
Standardized normal, likewise, standardized normal distribution we are using now, standard normal.
Right.
Just I thought in such a way, sir, how far it is suitable for this one, sir?
So basically, we are assuming that in a global nature of the data, there are localized part. In each localized part, we have an oscillation. So individual localized part is first picked up by using the appropriate wavelet function, and then they summed up. So you are right in that way that obviously wavelet is oscillates around that zero. So a data set, the whole global nature of the data is bifurcated in the several parts. Each part is considered as a single peak. Yeah, and that oscillates around zero. So that part is picked up. Then again move to the next part. That part is picked up, and this way it just summed up the whole part.
Sir, are we assuming that all these are additive in nature? All the parts should.
We are assuming in that way, because whatever decomposition we do, either wavelet or Simdan or other decomposition, generally we assume that all the parts are additive in nature, so that the pattern we can extract an individual pattern can be adapted.
Sir, is there any problem while going for forecasting by using wavelet decomposition models when compared to traditional models, sir?
Problem? No, there is no problem. Only assumption is that we have to have a large number of observations. For example, if you have 20-30 observations, there is no means to go for the decomposition technique, because in that, with 30 observations, if you go for the decomposition, bifurcating a series into several parts, may not be individual part will be having some individual or distinct pattern. So to have the distinct pattern existed in individual counterpart, we must have a large amount of the data. That's the main assumption. Otherwise, there is no disadvantages as such.
Sir, can this wavelet model is applicable in the presence of extraneous variables, sir?
Exactly, ma'am. You can do that, because we are concerning about the response variable only. And then when we actually go for this bifurcation or decomposition on the response variable, then individual subseries is correlated, or we try to find out the relationship between individual series and the auxiliary information. For example, W1, you are modeling. So
Yes.
W1 you model and you incorporate the information of the X. We do not go for the decomposition for X.
Okay.
As such. Yeah.
Okay, sir. Sir, how to identify the suitable wavelet activation function, sir? Is there any criteria for that?
There are criteria as such, it based on the number of observations and the level of decomposition. If our main interest is to go for the forecasting, then we generally restrict ourselves to go for the mid level of decomposition. For example, the highest level is 7. Though if our interest is to go for the trend estimation, then we go for the 7 filter.
Okay.
7 level. So accordingly, there is a filter. But if you go for the prediction purpose, then instead of going for the highest level of decomposition, we go for the mid level. Say, for example, the mid of the 7 is we take as 4, like that.
Sir, is Taylor diagram helps us in finding optimization or comparison of model efficiency?
It is for comparison of model efficiency. It is not optimization. It is just way of representing your MAP, RMSE, and all those things in visual pattern. Just
My
to
final question out of my ignorance is it compulsory to go for first linear model, then the remaining non-linear model, sir, as the part of two-stage modeling?
Yes, that is the methodology which Chang proposed, that only the linear part has to be extracted first, and then whatever remains, because we do not know, other than linear, there may be, for example, quadratic portion available. There may be some, sigmoid kind of things. They may be intrinsically non-linear. Exactly, they may not be non-linear, but they can be transformed to the non-linear part. So that's why it is proposed that only linear part will be extracted first. Then whatever remains, we go for testing the non-linearity, and then we can apply the non-linear part.
Okay, sir. Have you developed any R code in this regard, sir, especially for wavelet model?
Yes. All the packages, whatever we have shown, they are our developed packages, and they are available.
Oh, nice. Thank you.
In the presentation, the last slide I have shown,
Yes.
all the packages we have developed, and they are available. And the recent package is OptiSemble. I told that all the 13 model, all 20 optimization techniques are there. You just put your data. It will take some time, because all the optimization techniques will be called for all the different 13 models will be applied, individual weight will be assigned. So it will take some time, but it will give you the output.
Thank you so much, sir. I can stop my questions because it has very very full-fledged length of queries. I can solve all those in future, sir. I request the future support also from you regarding
Sure.
this
Yeah.
particular modeling, sir.
Thank you.
So please proceed for
Yeah.
practical sessions.
Yes, ma'am. Yes, ma'am.
Thank you so much.
So I'm just let me share the screen.
Sorry for troubling you for continuous sessions, sir, because after listening to theory only, we could do some practice, sir.
Right, ma'am. Right, ma'am. There is no problem, ma'am.
That is
No problem.
the way we planned, sir.
Yeah. No problem.
Thank you so much.
It's perfectly all right, ma'am.
Okay, thank you.
So though the program is already written, I have written it, and I'll just go slow. Those who are doing with me, I'm just sharing. Can I share it with the chat box, the data, if you want to do it with me, if anyone wants to do it me. So I'm just.
I hope it is not possible to do with you, sir, at this short period. But we can observe, sir. Later, you please share the code. I can share to all the participants.
Okay.
If they have reasonable doubts, they can contact you, sir.
Sure.
Help us. Thank you.
Sure.
Thank you.
So I hope this slide is, the screen is visible.
Yes, sir, it is visible.
Okay.
It is visible.
So the data set which will be, which we have taken for empirical demonstration is that this a price data, that is a potato price data. We can take any data set for demonstration, provided that it has large number of observations, at least 100, because to apply the machine learning and deep learning technique, 100 observations is the minimum. Though this is a subjective, very thumb rule. There is no as such theoretical consideration that this many observation has to be required. But yeah, this is the plot. So first of all, before we analyze the data set, the first step for a data analyst is to visualize the plot, visualize the pattern existed in it. So as we know, we all know that this potato, tomato, onion, all these perishable vegetables, even most of the agricultural commodity prices, they are seasonal in nature. So when we are taking into consideration the monthly data, and if you look at this visual plot, you may pick this particular feature, seasonality, that in a particular month, the price goes high, and that may be during August, September, and then it goes down. So this is basically the seasonality, and that seasonal part we may take care so that we can go for some improvement in the accuracy measurement. Now, this is the data set. Total 5 markets data are there. I'm just taking the data set in R. I'll give it a little zoom in so that you can see it properly. Yeah. So I hope a basics of R knowledge is with all of us, and you have different ways to import the data set. In whatever way you are comfortable to import the data, you import the data first. For example, I have kept my data set as CSV format, and I am comfortable in importing the data like this, read.csv. If you want Excel, then read Excel and then go for read.table, all these things. There are many ways to import the data. That is not the important thing here. So I just import the data, all these 5 markets data. Next, we go for attaching the data set. I'm sure that you all know what this particular statement means. Attaching the data means whatever variables are there in my data set, all the variables are now available by their name to call for. For example, I have these variables. It is printed here in the console. You can see Agra, Ahmedabad, Bengaluru, Delhi, and Mumbai. These are the 5 markets. These are the variables I have named. If I run this attach statement, now I can call Agra as by its name itself. So if I just write down, say, summary of Agra, so I can get the different statistical measures for this Agra market data. But if we do not run this attach statement, and if I call this Agra, it will give us an error message that Agra is not found. So that is the purpose of attaching the data set. Once we import the data, you go for attaching the data first. Then the libraries which will be requiring for our analysis. One is the T-series package. These are all well-known packages, those who are working in the time series domain. One is T-series package. It is for testing the stationarity like ADF test, for BDS test, testing the non-linearity, all these things. T-series package is very much useful. Then we have a package called fgarch. You know, R is case insensitive in nature. So you must be careful when you are writing the upper and lower case letter. So library fgarch, this is for application of the Garch model. Then we have library FinTS. This is financial time series. Again, it is for application of the nonlinear time series model along with the testing of arch effect and all those things. One more library is forecast, which is very famous in time series domain. It is for application of the ARIMA model, exponential smoothing model, ANN technique, and all those for the forecast package. So these are the few packages which we need to load it before we go further. So let us load this package. Sorry, T-series. Sorry. Yeah. So T-series, then fgarch, we have FinTS, we have forecast. These are the 4 packages we have to load it. Now we have already loaded the data. If we know the number of observation in the data or what are the names in the data, we can just print n row of data. We have total 211 observations in it. We have total 211 observations in it. Okay. Now, we have a Y, that is the time series data. And in this particular data set, we have 5 variables basically, but we have to choose one variable at a time. We cannot, because whatever models we will be applying, they are all univariate in nature. Either ARIMA, GARS, ANN, random forest, SBR, GBM, LSTM, GRU, RNN, whatever model we apply, all the models we will be applying on univariate data set. So it is better to start with a single variable data. So for example, the second column, that is the first market data. If you see the data set, it has date and then different markets. So second column data, I'm just choosing. It is monthly data. I have given the data set reference. Frequency equals to 12. That means it is a monthly data. That means in a year, there are 12 entry. And the starting year is 2005. So this way we can make a time series data, because R does not know that whether the data we are dealing with, it is a time series data or is a regression data. There is a significant difference between regression data and time series data that we know. I am sure we all know that regression data, the observations are independent in nature. In time series data, the observations are dependent. So that is the most important distinction between these two data. The regression data can very well take care of missing observations, but time series data cannot take care of the missing observations. If you have any missing observation in between in a time series data, and if you delete it, that means the continuity is broken. The ordering of the observations is hampered, which is not desirable. But in case of the regression data, if you have a missing observation, you can just omit that whole row and it will not affect the final estimate. But in time series data, if you just miss any observation in between, it is basically affecting the ordering of the observations, which we assume that the observations are dependent in nature over the time point. Okay, so that's why making a time series data is important before we run a time series model. Then we can go for plotting it to see if we want to see it. Though we have already seen it in Excel, but now the most importantly, any of the time series model, either you are going for fitting classical time series or any machine learning techniques, we need to make two subsets. One is called training set, another is called testing set. So training set, we are just keeping these many observations for the training set, and testing sets, remaining set 12 observations I am keeping for the testing set. Now, the ARIMA model building, as you know that how to build up the ARIMA model, I am for to save the time, I have just called for the automatic ARIMA model building, though it is not advisable to go for. Whenever you try to fit the ARIMA model, it is always better to go for by following the procedure, by stepwise procedure, instead of going from automatic ARIMA model. Because if you go for this automatic ARIMA model building, it will be just giving you the best model based on one criteria, say either AIC or SBC or BIC, whatever criteria you choose. Based on that, the model which is having the minimum that value, it will give you the best model. It may not always come true, because in that it may happen that there are some parameters which are insignificant. So in that, it is better to go for the stepwise selection of the individual lag and follow the steps to perform the ARIMA model. But here our main purpose is not to demonstrate to fit the ARIMA model, rather to go for some kind of hybrid model. So that's why I have just called for the automatic ARIMA model building to get the ARIMA fitted value. So if you just go for this automatic ARIMA model building, auto.arima within bracket, you have to give the training data. Then if you put trace equals to true, that means whatever models are being applied, whatever different combination of the parameters are being applied, all those will be listed here in the console. You can see that these are the different combinations they have tried. For example, maximum value of AR lag is 2, maximum value of MA lag is 2. and all other combinations have been tried. 2, 1, 2, 0, 1, 0, 1, 1, 0, like that. With drift means with intercept. With drift means it is nothing but with intercept. So one criteria, this information criteria has been given, and it has chosen the model as the best model, which has the minimum information criteria, right? So once you have done it, then seasonality equals to true. This is, we have seen that the seasonal component exists in the data. So better to get the trend data as the seasonal, because we have made the original time series data as a seasonal, as the monthly data. But when we actually get this trend, we just took some observations from 1 to 192 rows of the data and passed it as a response variable in the ARIMA. So when we actually did it, it has no this seasonal component. To incorporate that seasonal component, I just keep it train 1, and on the training data, I have just run again that seasonal component. So this will give you some seasonal parameter also. For example, here you can see ARIMA 0, 1, 1, 0, 0, 1, 12. 12 is for the seasonal part. First parameter set is the non-seasonal parameter. Second parameter set is the seasonal parameter. And with drift, that means with constant, this is the best model. As this is not our main interest to go, but this is the prerequisite thing, because we need to compare the performance of the different model with this, the base model. We get the forecast for the next 12 observation, as because in the test data set we have kept 12 observation. That is why for forecast ARIMA I have given H equals to 12. So for the test data set, I want the forecast, because I need to validate the performance criteria for training as well as testing set. And in general, the testing set criteria is chosen, is preferred, because testing set is basically the data which is out of sample data. That data set has not been used for model building. So if your model performs well for the testing set, that means it is good. Your model is performing really good. Then we can extract the fitted value, and then we can get the accuracy measurement also. We can get the accuracy measurement. As I told initially that we can, if we go for this accuracy measurement, there are different criteria: mean error, RMSE, MAE, MP, RMSE, MAC, ACM, all these different criteria will be resulted, and you can choose the, you can actually visualize that how good your model is in picking up the pattern existed in the data. Now, as usual, once we have fitted an ARIMA model, we go for extracting the residuals, and residuals we have just stored in X. We have just called this function resid within bracket ARIMA model, that is model ARIMA, the output of the ARIMA model we have fitted. On this residual, what we need to do is that we need to go for the arch test. That is, arch test is also test of nonlinearity. That means if the variance of the error term is homoscedastic or heteroscedastic. That is for arch test, autoregressive conditional heteroscedastic test. Whether the variances of the error term is heteroscedastic or conditional heteroscedastic or not. For that, we need to call for this arch test. This is a keyword functionality available in FinTS package, financial time series package. Within bracket, what are the arguments we need to pass? One is the residual coming from the ARIMA model. We have fitted an ARIMA model, the residuals we have extracted, and that residual has to pass as an argument in this particular function arch test. Then we have to select different lags. So arch test at what lag? Generally 1 to 12 we go, because it is a monthly data. So 1 to 12, up to 12 lag, we can see if at any of the lag, this test is significant. That means there is a significant presence of arch effect, and we need to go for some nonlinear time series model. Okay, so we just run it. You will see that in the console, the result has come. The p-value is saying that it is 0.011. What is the null hypothesis? Null hypothesis is that no arch effect. That means homoscedastic error, no arch effect. But the p-value says it is less than 0.05. That means we are rejecting the null hypothesis. So no arch effect is rejected. That means there is an arch effect. That means non-linearity is present in variance. So we go for the GARCH model. We have fitted ARIMA first. we have seen that residuals are having arch effect. That means there is a nonlinearity present in the variance, or the conditional heterostaticity is present, and we need to go for fitting the nonlinear time series model. So we are just fitting guards now. This is the guards fit functionality we have to call for. Within bracket, you need to pass on the mean model. Mean model, you need to pass an ADIMA. Then guards model. What is the data set you are want to apply? Train data, obviously, whatever we are doing on the basis of the train data. Testing data is for the performance measurement. So once there are some warning messages there, that is not that important. So once you have fitted the guards model, it will give you all the different estimates. Okay. Here, see, you can estimate, you can see the estimate. We have, for the guards model, we have a mean. We have mean model as AR1, we have mean model MA1 coefficient. In the variance model, last three components are for the variance model. One is the constant for the variance model, then the arch effect alpha 1, then the guards effect beta 1. So arch effect, you can see 0.28, guards effect is 0.67 or 68, right? So here the condition is that these arch plus guards, alpha 1 plus beta 1, last two coefficient, the sum of this coefficient must be less than 1. That is the condition. For the guards model to be stationary, the condition is that these arch parameter and guards parameter, the sum of these two parameters should be less than 1, and both should be positive as well. So individually coefficient should be positive, and the sum of these last two coefficients should be always less than 1. So this condition we need to first look at. Then we can see whether it is significant or not. So individual coefficients are significant. P value you can see 0.00. In the beta 1 also it is very close to 0. So as we have already seen, there is a significant arch effect present in my residual series coming out from the ARIMA model. Accordingly, we have fitted guards model, and the guards model, all the parameters have to be significant. Then we can get the fitted value for this fitted model. We can get the forecast also, right? For the 12 observations, because in the test data set, we have kept 12 observations for the test data. And then it's, the different criteria, accuracy measurements we have to compute. We'll compute in the latter part of it, we have there. Now, so this is guards. One, we have applied ADIMA, extracting the residual. And on the residuals, we have checked for the arch effect, and we have seen that there is a significant arch effect. Accordingly, we have applied guards model. Now coming to the neural network or machine learning technique. So here from, it is a application of machine learning technique. I'm just writing it. Application of neural network model. So the package is forecast itself, which we have already loaded in the beginning. The function is NNETAR. NNETAR is the function. The package is forecast. Within bracket, you need to pass the response variable followed by different parameters and hyperparameter. As I told, so here comes our input, that it is whether it will be 12 or 10 or 2, that we need to decide, right? So this is nothing but non-seasonal lag, P equals to 12. That means in the non-seasonal counterpart, present depends on how many lags. In general, if it is a monthly data, we see up to 12. All the values we need to check 1, 2 up to 12. And then we need to note down this RMSE, and then we have to pick up the particular value for P for which this RMSE is the minimum. Similarly, we have a hidden node size. Okay, they are here also. In general, it is P plus 1 divided by 2. So 12 plus 1 divided by 2, that is 6 or 7. So within 6 or 7, upper side and lower side also, different values we need to try, and then we need to come to the optimized value, that which minimizes the root mean square error. So I have done few exercises, and then I have come that this particular model combination gives the lowest MSE. So this is NN. If you just put this, this is the structure. This is sigma estimate. And then if you go for the forecast, so here it is 12, not for 24, because in the test data set, we have only 12 observations. Then you can go for the accuracy measure as well. So 3 models you have applied till now. One is we have applied ADIMA. We have checked the residuals. We have applied GARS. We have applied ANN. And then on the, before we apply ANN, we can go for again that non-linearity test, which we have already discussed, that once we have applied an ADIMA model, we extracted the residuals. On the residual series, we need to apply the test called BDS to see whether any significant non-linearity present in the residual series of the ADIMA model or not. So for that, we just extract the residuals of the fitted ADIMA model. We go for the BDS test, and we can see that these are significant, 0.05, or at the borderline 0.04 is there. So this p-value less than 0.05 means that it is significant, or significant non-linearity is present at 5% level of significance. So accordingly, ANN has been fitted, and then we get the ANN forecast, right? And for the final forecast, so whatever we have got for the ADIMA, on that forecast, we are just adding the forecast coming from the ANN on the residuals. So both the forecast will be added to get the final forecast. And if you want to measure the different accuracy measurement, for example, mean absolute percentage error for the training data, for testing data, similarly RMSE for the training data and testing data, like that. So here in the argument, you can notice that final fitted within bracket minus C1 to 12. When we have fitted the ANN model with 12 lags, the first 12 observations prediction value we cannot get. So that is why first 12 observations we are just removing for the actual data also, so that we have the same observation for the actual and the fitted, and we can compare both. That's why this minus C1 to 12 is here. Then coming to the decomposition, at the last, we just compare all the different models for their accuracy comparison. So as I told, different packages have been built up. For example, wavelet ADIMA, you go for wavelet decomposition followed by application of the ADIMA model. That package named is wavelet ADIMA, which we have built up. Then we apply that model. All these are available in this particular package. You need not to remember this functional form also, I mean the code also. You just go to this wavelet ADIMA package and you will get this function, copy that function, paste it here, pass your own data, train here, and the remaining arguments, they may go as default. Also, you can change it. For example, number of forecast, I want 12 here because in the test data, I have 12 observation. You can change it. I have given maximum air parameter to be at 5, maximum MA parameter to be at 5. So you can change it. Maximum air parameter, MA parameter, it may be 2, 3, or like that. So these are the different arguments which we can change. Then similar package is wavelet ANN, that means decomposition followed by application of the ANN. Apply for all these same function. Instead of wavelet fitting ARMA, now it is wavelet fitting ANN. Arguments are also same, very similar. Then third one is GARCH. Similarly, we have wavelet SBR, wavelet RV, RF, wavelet GBM, wavelet LSTM, like that. Different decomposition followed by your machine learning and deep learning technique, as well as classical time series technique. This is for wavelet GARCH, that we go for wavelet decomposition, and each decomposed series, wherever there is a ADIMA linear part, you go for linear fitting ADIMA, and wherever there is a non-linearity, you go for fitting the ARCH model or GARCH model. So that way you can get this wavelet GARCH forecast. It is it takes little bit time for this GARCH model, because what it does is that it decomposes the data set, and then on each of the decomposed series, it first investigates whether the pattern is linear or non-linear. If it is a linear pattern, then it goes for fitting ADIMA model. If it is non-linear, it goes for fitting the GARCH model. So this way, it actually applies different models to different sub-series. And then for accuracy measurement, we have ML metric package, This is a well-known package, ML Matrix, very old package, from where different accuracy measurement like RMSE, MSE, MAE, MAP, ME, different accuracy measurements we can print and we can compare. Otherwise, also we can go for writing down the formula to compute the different values. So, for example, MAE ARIMA, what is that? MAE GARCH we can compute. MAE ANN for the ANN model. For the wavelet forecast ANN, then wavelet ARIMA, wavelet GARCH. These are the 6 models, right? And then if I just want to compute all these mean absolute error in one go. So here you can see the performance measure or the accuracy improvement. We have actually fitted ARIMA or in fact SARIMA, seasonal ARIMA model. For that, MAE has 2199. Now on this, instead of simple ARIMA, you go for wavelet decomposition followed by application of ARIMA. So your accuracy is gained almost 50%. From 2199, it reduces to 1500. Similarly, you have a GARCH on the individual series, original series, you have applied GARCH model. It has given you 675 MAE. Now, instead of fitting the original series GARCH model, we go for decomposition and followed by fitting the GARCH. So 675 reduces to 575. Similarly, ANN, in original series, if you go for fitting ANN, it is this much. If you go for decomposition followed by ensemble with ANN, then it reduces to 300. So everywhere, wherever you are going for kind of ensembling, either with decomposition or ensembling with different models, then your accuracy will be improved, definitely. Similarly, for other criteria like MAP. If you print it once, you can see the decrease, you can see the improvement. The original counterpart, either ARIMA or GARCH or ANN, according, and then the ensemble counterpart. So everywhere you can see that there is some improvement in the particular accuracy measure. Similarly, we have RMSE. So all these things are written, and I shall share with you all this. So here also, in case of the RMSE, as I told initially, it is always better to go with simultaneous criteria, different criteria simultaneously, so that we are in the safer side to give the consistent model, more consistent model or robust model for the prediction purpose for a particular series in hand. So here you can see the everywhere, wherever you have gone for ensembling kind of thing, we have gained a significant amount in accuracy measurement as compared to the individual standalone model. So for this demonstration, I have not considered this deep learning technique because it takes time. We have the packages also, all the packages like Wavelet LSTM, TS LSTM, different packages are made, they are available. So you just try it, whoever is interested to apply this model, you try it to demonstrate as it requires few time, because deep learning model, even if simple deep learning network, if you apply, it will take some time to give the output. So that's why I have not included it here, but you are free to apply as all the packages are available in the CRAN, and our packages list are also there. So you apply it, and if you face any difficulty, anytime you can just ping me, let me know, so that we can discuss and solve it. So that is in brief, madam. And I think it is a long session. So
Yes,
I was going a little rapidly to some of the things. Sorry for that, but yeah, I'm always open if anyone is applying this model or any other statistical model for their data analysis. If you face any difficulty, you just let me know. If I am not the right person, then I will let you know who is the right person, or I will consult with that particular expert.
Thank you so much for your consent, sir. Thank you so much for your consent, and very good lecture and a very deep lecture, sir. This is deep lecture in terms of forecasting as well as non-linearity and machine learning is concerned. Sir, by this, we have a couple of queries.
Yes, ma'am.
I can pose. Sir, how to identify, one person is asking here, they have sent a message to me, how to identify the appropriateness of the wavelet activation function, which is already asked by me. Told that you need to go for several iterations, permutations, then you can
Yes.
check with
For,
that.
for the first time user, I suggest not to bother about that.
Yes,
Just
sir.
default the most crucial or most trivial wavelet is the HAR wavelet.
Sir.
HAAR, HAR. This is the most trivial wavelet filter which is available. Even this particular filter will also give you gain in accuracy as compared to the individual counterpart. But there are other filter like D4, which is called Dovec's, Simlet, least asymmetric. There are many, in the list. Once you have applied HAR, you are accustomed with this, then you go for choosing the different filters and see how it is behaving.
Okay, okay. Then final question is there. Then clustering and decomposition numbers is there, sir. You told that depending on the sort what they are telling, and wavelength you are taking numbers, sir, 7 or 8 number like that.
Yes,
How
yes.
to decide that fixed number they are asked?
Yeah, that is the formula is log of n base 2. Log of n is the number of observation.
Is it available in PPT, sir?
Yes, it is available.
Yeah.
It is available.
Okay.
I'll share with you, but just to answer, the log n is the formula.
Okay.
Logarithm of number of observation base 2, and the integer portion is the highest. So if it is 7.2, the 7 is the maximum level of decomposition. And then again, I told that if our purpose is to go for prediction, go for the minimum mid level. If it is maximum 7, so go for mid, that is 4. If our purpose is to only trend estimate, then you go for the maximum level, that is 7.
Okay, sir. Is there any possibility to have only 2 linear models in a 2-stage modeling, sir? Is it possible?
2 linear model.
Yes, sir.
That means first we apply linear.
Yeah, linearity and leftover thing can be done by another linear model. Is it possible?
No, this should not be, because once you have applied the linear model, if that model has been built up adequately, then no linear portion should be left out.
Yeah.
So if there is any linear portion left out in the residual, that means the first model, whatever we have,
One is not good.
that is inadequate.
Okay.
Yes.
Thank you so much, sir, for your patience to dispose the knowledge and in a very smooth manner, even though this is a very tough topic. But it is very beginning to us, sir. Definitely, on behalf of all the participants and the Department of Statistics students are concerned, I am promising you we can work on this to have the very accurate and precise estimations as far as agriculture sector is concerned, sir. Then by this, now I request our young faculty of our department, Dr. G. Sambasiva, to propose a formal vote of thanks on this regard. Before that, I have an announcement, and after sharing, when we get the PPTs and the code from the speaker, immediately those can be shared to all the participants. Please go through once again PPTs for the theoretical knowledge and work with the R code. It is clearly written with the headings also, with the messages also. Based on that, definitely we are going to get the precise and accurate estimations as far as modeling is concerned. Thank you so much, sir. Now over to Dr. G. Sambasiva.
Thank you, madam. Honorable dignitaries, respected sirs and madams, and dear participants, a very good evening to one and all. On behalf of Department of Statistics and Computer Applications, SV Agriculture College, Tirupati, and organizing committee, I feel immense pleasure to take this opportunity to propose vote of thanks on this national webinar on hybrid artificial intelligence models in agriculture. I sincerely express my gratitude and hearty thanks to Dr. A. Vishnuvarthan Reddy Garu, Honorable Vice Chancellor, Acharya N.G. Ranga Agricultural University, for his continuous encouragement in conducting webinars for the benefit of teachers and students. I take this opportunity to specially express my deep regards and gratitude to Dr. P. Sudhakar Garu, Dean of Agriculture, Acharya N.G. Ranga Agricultural University, for his encouragement and provided an opportunity to organize this national webinar to the Department of Statistics and Computer Applications, SV Agriculture College, Tirupati. I would like to thank Institutional Development Plan, IDP, ANGRU, for necessary support in conducting this national webinar. Further, I would extend my gratitude and thanks to Dr. G. Prabhakar Reddy Garu, Associate Dean, SV Agriculture College, Tirupati, who is the guiding force behind organization of this webinar with his able guidance. I would like to express my sincere thanks to Dr. P. Srinivasarao Garu, Professor and University Head, Department of Statistics and Computer Applications, and also Associate Dean, Agriculture College, Bapatla, for his opening remark on this topic and his encouragement and suggestions when and then it is required. Further, I would extend my gratitude and sincere thanks to Dr. Ranjit Kumar Pal sir, Senior Scientist, ICAR, Indian Agricultural Statistical Research Institute, New Delhi, for today's couple of topics on need for hybrid artificial intelligence models in agriculture and hybrid artificial models using R program. Who gave more information and applications of hybrid artificial intelligence models in agriculture sector in a simple and excellent manner. Once again, thanks to you, sir. I extremely thanks to the convener, Dr. P. Lavanya Kumari Madam, Assistant Professor and Head, Department of Statistics and Computer Applications, and Dr. Sheikh Nafiz Omar sir, Assistant Professor and our Organizing Secretary and other Co-Organizing Secretary, Department of Statistics and Computer Applications, SV Agriculture College, Tirupati, who worked with a team spirit to conduct this seminar. Our sincere thanks to the teaching and non-teaching staff who are cooperated successfully conducted this webinar. My deep sense of appreciation and thanks to all the participants for attended this webinar and made it successfully. Not least, my hearty thanks to the students G. Harish, Indruhi, Sevprasad, Shaitas Banu, and K. Jnam Prakash for their technical support to the conduct this national webinar from the beginning to the end. Once again, I heartfully thanks to all, each and everyone who made a successful event. Thank you. Thank you, one and all.
Thank you, sir. Thank you.
Thank you. I once again thank all the participants for their patient listening, and it is very wonderful topic, sir. Definitely, with this enlightenment, definitely we'll go ahead to have the precise and very good forecasting models as far as agriculture is concerned. Thank you.
Thank you, ma'am. In a short while, I'll just share the slides and code with you. You may share with the participants.
Sure, sir. Sure. Thank you so much, sir.
Thank you.
So much.
Thank you, sir. Thank you.
So much. Thank you, sir. Associate Dean, sir. We are closing the session, sir. If you are online, thank you, sir. Associate Dean, sir. Okay, sir. We'll
Okay.
the program. Thank you so much.
Thank you.